Hello, welcome back to Learn Physics. In today's topic, we are continuing with our magnetism and matter. In last video, we learned about the terms in magnetization in that chapter, which are the major terms which we are using. That one we learned. So, including all those terms, today we are going to find a relation connecting the magnetic permeability and magnetic susceptibility. So, the relation connecting magnetic permeability and magnetic susceptibility. So permeability means it is mu and susceptibility is chi m. So we are going to find out a relation connecting these two. So for that, so the relation connecting mu and h. So to find out that one, I am just reminding you about the terms which we used in the last video. So first one we learned about B, magnetizing field strength. Isn't it? Field strength we told. It's magnetizing field strength. Then H, magnetizing force. Magnetizing force or magnetizing force. And so these two are the major terms which we learned in the last class, isn't it? H is magnetic field strength and H is the magnetizing force. Okay, so if this magnetizing force is for a magnetic material, this magnetic field strength is for a magnet, isn't it? This is for B is for a magnet and H is for a magnetizing material. Now, if I am a magnet is present or magnetic field is present, a magnetic material also there, a magnetic material also there. So what will be the total magnetic field or magnetizing field strength of the magnetic material? See, that will be due to the vacuum present over there plus due to the magnetic material, magnetization produced by the magnetizing material and magnetization due to the vacuum. So this B equals B0 plus Bm. So what is B? B is the total magnetic field strength or magnetic field strength due to the presence of a magnetic material. Okay, magnetic material is getting a magnetization. That magnetic field strength is B. That field strength is the vacuum produced by the magnetizing field strength and the magnetic. Because of this magnetic material, it is getting some magnetic field. So what is the total magnetic field? B equals B0 plus Bm. So B0, how we can write it out? That will be equal to mu into. So B in last class we wrote it as B equals mu into Ni. This Ni we can write it as H. Isn't it? You are remembering, right? B equals mu into H. Okay, therefore we can write it as B0 equals mu 0 into H. So instead of B0, what I can write it? Mu 0 into H. Now Bm. How we can write down this Bm? This Bm equals mu 0 into I. Okay, so here we can write it as B equals mu 0 into H plus mu 0 into I. Okay, from here we can take mu 0 outside, that is H plus I. Now we have a relation connecting chi and S. Chi equals I by H. From there we can write it as I equals chi into H. Therefore, mu 0 into H plus, instead of I can write it as chi H. So, mu 0 into 1 plus chi into H. But we know, see, B mu equals mu 0 into 1 plus B equals mu 0 into 1 plus chi into H. B equals mu H, we know, right? Mu H equals mu 0 into 1 plus chi into H. So H and H will get cancelled. So we will get it as mu equals mu 0 into 1 plus chi, or we can write this as equal to mu R. So understood, all these formulas are important only. So I'll explain you once more. Here we are going to find out the relation connecting magnetic permeability and magnetic susceptibility. So in the presence of a magnetizing field, we are going to keep one magnetic material. So material is getting some magnetic field. What will be the magnetic field? Magnetic field which it is acquiring for the magnetizing material will be equal to magnetic field due to the vacuum. Okay, due to vacuum it is getting some magnetic field plus due to the magnetic moment. Okay, so due to the magnetic material, it is how much magnetic field strength is acquired by the magnetic material. So B equals B0 plus Bm. Got it? What is the total magnetic field strength of the material? We should, along with the material, we should consider the magnetizing field due to the vacuum also. So B equals mu and I. This formula we already learned, isn't it? So we can write it as B equals mu into H. B0 equals mu 0 into H. So instead of B0, we can write it as mu 0 into H, and Bm. What is Bm? It will be mu 0 into I, magnetic material. In a circular loop, we know it as we already learned in the last class. In the case of solenoid, B equals mu 0 Ni. For if the number of turns is considered as 1, then we can write it as Bm equals mu 0 into I. So here we can take mu 0 outside, H plus I, and I we already wrote it as chi is the ratio between the intensity of magnetization divided by H, isn't it? So magnetizing force is H. So H is, we are taking it as common, B equals mu 0 into 1 plus chi into H. So we are getting it as, but B equals mu into H. And mu HH will get cancelled. We will get it as mu equals mu 0 into 1 plus chi. So here we are getting the major equations like B equals mu 0 into 1 plus chi into H, and mu R equals 1 plus chi. These are the main equations which we are getting from this relation. So here what is the relation connecting mu and H? Mu equals mu 0 into 1 plus chi. So what is the relation? Mu equals, so one more here, mu equals mu 0 into 1 plus chi. That is the relation connecting mu and chi. Clear? Next we are going to study about the classification of magnetic materials. So magnetic material means when we are placing a material in a magnetic field which is getting some magnetic moments, magnetic properties it will be getting. They are called magnetic materials. So today we are going to study about the classification of magnetic materials. So first one is Faraday did this classification according to the property of the magnetic material. So first one is diamagnetic material. Diamagnetic material. What is meant by this diamagnetism? Suppose a magnetic material is here. I am giving an external magnetic field to this magnetic material. So if it is a magnetic material, what will happen? That will be getting some magnetic properties. This also will acquire some magnetic properties it will acquire. But if it is a diamagnetic material, it will be repelling this magnetic field. It will repel this magnetic field. That means while we are giving magnetic material, what will happen? It will go out, it will repel. That is, the magnetic field will be moving from stronger to weaker part. So this magnetic field strength, in which direction it will go? Towards the weaker part, weak side it will move. So it will repel out, it will be repelling from this magnetic material. So it will be having least magnetic properties. Okay, so clear. So if we are giving an external field, what will happen? It will repel. It will repel means it will move towards the weaker part. Okay, weaker part of the magnetic material. Okay, magnetic property, which is where it is weaker, there it will be moving. Okay, it will be moving from stronger to weaker part of the material. Okay, so it will move out. So what will be the reason? Okay, a simple explanation how we can give it for this diamagnetic material. So in the case of this diamagnetic material, it will be electrons are there. Every metal, it will be having electrons, will be revolving around in a circular orbit. It will be moving in a circular orbit. So it one we can consider as a current carrying loop. A current carrying loop will be there. So it will be having some orbital angular momentum. It is moving in a particular angular momentum, and it will be having orbital angular momentum. Okay, if we are not applying any external magnetic moment, any external magnetic field to it, then the total magnetic orbital angular momentum will be equal to 0. If B is equal to 0, total magnetic moment also will be equal to ML. Magnetic moment will be equal to 0. While we are applying magnetic field, what will happen? This will be repelling, I told, right? So this magnetic moment, orbital angular momentum, this orbital angular momentum will be mu L, orbital magnetic moment. What if we are applying a magnetic field? What will happen? Orbital magnetic moment. So not angular momentum, magnetic moment. Orbital magnetic moment, which is having in the same direction, will slow down. In same direction will slow down. And if magnetic moment in the opposite direction will become fast. Okay, so if we are not applying any magnetic moment, total magnetic orbital magnetic moment will be equal to 0. Actually, how the total magnetic moment is getting 0? Orbital mu L and mu S. Together it is getting 0, not like mu L alone. Okay, so total magnetic, not mu, M. ML plus MS will be equal to 0. Total magnetic moment will be equal to 0. How this total magnetic moment will be equal to 0? Along with this orbital moment, it will be having some spin also. It will be spinning also. It will be moving in an orbit. Same way it will be spinning also. So because of these two magnetic moments, sum will be equal to 0, since they are in the opposite direction, if no magnetic field is applied. So clear, right? So if we are not applying any magnetic moment, what will happen? The net magnetic moment will be equal to 0. That is, orbital moment plus spin moment will be equal to 0. If we are applying some magnetic moment, what will happen? Magnetic moment which is moving in the same direction will be slowing down. The electrons which is moving in the same direction will slow down, and which is moving in the opposite direction will move faster. Since it is opposite direction, so what will be the net field there? Net magnetic moment, in which direction it will be moving? Net flow will be in which direction? Opposite direction. Net will be in the opposite direction. Okay, so that is the reason for repulsion. Repulsion of magnetic field, why it is happening? Because while the magnetic moment is if we are applying magnetic field, in the case of diamagnetic substances, the magnetic moment which is moving in the same direction of magnetic field will be slowing down, and which is in the opposite direction will become faster. So while we are considering the net magnetic moment, what will happen? Net magnetic moment will be in the opposite direction. Opposite direction direction means it will be moving out. That will be the cause of repulsion in the diamagnetic substances. Okay, clear? So in the case of a diamagnetic substances, net magnetic moment will be equal to 0 if we are not applying any magnetic field. While we are applying magnetic field, magnetic moment in the same direction of movement of electrons will be slowing down, and which is in the opposite direction will become faster. So what will happen? The net magnetic moment will be in the direction of opposite to the direction of magnetic field applied. So opposite to the direction, when it is moving, what will happen? It will be the repulsion. It will be the so that is the reason we are telling it is moving from stronger to weaker field. Clear? The magnetic moment in the case of diamagnetic material, how the magnetic moment is moving from stronger to weaker field. So always remember, in the case of this diamagnetic material, it will be moving from stronger to weaker field. Okay, so now what will be the mu value and chi values here in this diamagnetic substances? Chi is less than or equal to -1 or less than 0. But in the case of mu r, first we will be writing about the mu r. Mu r will be less than or equal to 0, 1. Okay. So maximum value of mu r will be in this region between 0, which will be equal to 0, can go up to 1. Okay, it will be below 0, and this also will be like this. Okay, clear? So this values will be between 0 and 1. Chi and mu r values will be between 0 and 1. And the best diamagnetic substances are superconductors, are considered as the best exotic diamagnetic substances. Okay, example for this is copper, gold, silver, and bismuth. All these are diamagnetic substances. Okay, but in the very good diamagnetic substances are called as superconductors. Superconductors means what will happen if we are reducing the temperature. While we are reducing the temperature, the resistance will become equal to 0. When if temperature is reducing, what will happen? Resistance will be equal to 0 and will be getting repelled. Perfect repulsion will happen over there. And if temperature is reducing, if we are reducing the temperature, magnetism it is fully getting repelled. When it is getting repelled, that is, it is showing perfect diamagnetic properties at a low temperature. At low temperature, it will show perfect diamagnetic property, and this was given by the scientist Meissner. So it is called as Meissner effect. Okay, yes, diamagnetic substance, the superconductors which shows that perfect diamagnetism, it is called a this Meissner effect. Okay, so it is if temperature is becoming equal to 0, what will happen to the resistance? Resistance will become equal to 0. If temperature is reducing, what will happen? This resistance will be equal to 0, and magnet will be showing, the diamagnetic material will be showing the perfect repulsion over there. Okay, when the diamagnetic substances are repelling the magnet also will be repelling the diamagnet, isn't it? So equal and opposite reaction as per Newton's third law. So here this is called as Meissner effect. So in the case of diamagnetism, since mu r will be equal to showing perfect magnetism, isn't it? So mu r will be equal to 0. If mu r is equal to 0, what is the value of chi? Chi will be equal to -1. Okay, so here, sorry, this is -1, 0 and -1. Okay, so chi will be equal to -1, and this chi will be equal to -1, mu r will be equal to 0. This is the properties of a diamagnetic substances. So I'll tell you the important points of this diamagnetic material once more. In the case of diamagnetic materials, when we are applying an external magnetic field, what will happen? It will move from stronger to weaker field. That is first point. It will be moving from stronger to weaker field. And what will happen, what is actually happening inside the magnetic material, diamagnetic substances? Total magnetic moment is equal to 0 if we are not applying any external magnetic field. That is how it is. M is equal to 0. Orbital magnetic moment and the spin magnetic moment together, it will become equal to 0 if B is equal to 0. Orbital magnetic moment means electrons are revolving in a particular orbit. Then if we are applying B, if we are giving B, what will happen? That is magnetic field while we are applying. Electrons which is revolving, which is having the same magnetic moment, same magnetic moment will slow down, and electrons having opposite magnetic moment will moves up slow, it will speed up. So together, while we are considering which will be having more velocity, it will be having the net will be acting in the direction of opposite direction, because electrons which are moving in the opposite direction is faster. So net effect will be for the opposite direction. That causes a repulsion. So that is the reason of repulsion of magnetic moment in the magnetic field in the case of diamagnetic substance. Okay, clear this? Now, best example for the, now this is the condition. This relative magnetic permeability, that is between 0 and 1. Okay, it will be less than 1 up to 0 it can be. Chi means it will be -1 to 0. Clear? This is clear, right? Now, best example is superconductors. Copper, gold, silver, bismuth, all these are examples only. But best example is, so all the superconductors are best example for diamagnetic property. If temperature is, if we are reducing the temperature, what will happen? R is equal to 0. If resistance is equal to 0, it will be, the magnetic properties will be, it will be fully repelled. Magnetism will be fully repelled for the superconductors. Okay, if that is complete repulsion. In all the diamagnetic material, this complete repulsion won't happen. It will be a weak magnetic field will be there inside. Okay, but in the case of superconductors, if it is near reducing, what will happen? The resistance will become equal to 0. It will be very good conductors, and diamagnetism will be, it is a perfect diamagnetic substance. This property is known as Meissner effect. Okay, in the case of this superconductors, mu r, relative magnetic permeability is equal to 0 and chi will be equal to -1. They are the maximum. They can, mu r can reach up to 0 and chi can reach up to -1. So these are the maximum values which is applied for a superconductor. Okay, clear? So this diamagnetism and the relation between mu and chi, that also clear for you. Mu equals mu0 into 1 plus chi. So all those terms which we learned in the last class, and this also important only. This, all those terms, any one question you can expect from that portion, that terms and its dimension and its unit, all those are important. Okay. So I hope all of you are clear about it, and we will be continuing in the next class with the paramagnetism and ferromagnetism and hysteresis curve. Okay, so winding up for today. So I hope all of you understood all those things. If you like the channel, please don't forget to subscribe. Thank you for watching. Bye.